Kagglers. I'm just gonna really quickly check my audio. Make sure it's sounding good. Okay, that sounds pretty good. Wait for the stream to catch up for me like I usually do. And really quickly just tweet that we are getting started. Sorry, I had a really interesting morning on Twitter because yesterday I tweeted something about vision versus language, and I've gotten some really interesting and helpful comments, and I've learned a lot. So I was distracted a little bit by Twitter this morning. Whoa, Cat Blocks is on. Getting started with part 2 of Deep Learning for Symbolic Mathematics. Symbolic Mathematics now. Okay, audio sounds good. Good morning for me, whenever it is for you. I hope you're having a good one. We are going to be kicking back off with this paper, Deep Learning for Symbolic Mathematics. That's not centered. There we go, much better. And this is a paper from, I think I said ICML at some point. It's actually ICLR, so the International Conference on Learning Representations. And it is a paper looking specifically at solving equations. So I believe they were, it's been a minute since I looked at the paper. I believe the equations that we were solving were, it says right here, symbolic integration and, solving differential equations is one task, and then symbolic integration is the second task. And a little refresher of what we read last week when we, I forgot to have everybody up. Hello, everybody who has joined. What we read last week, that's very small. Let me make it a little bit bigger. What we read last week was the sort of general premise of the paper. And the idea is that they are taking equations and they are expressing them as trees. And the trees are a combination of binary and unary trees, so there can be up to 2 branches per node. And it looks like they are, and this is because of the way that they formulated the problem. So going even further down for their list of rules, the data set for this is actually generated. So they generated the solutions, and then they generated the problems from the solutions. And the sort of algorithm that they used to generate those problems and also solutions were trees with up to n internal nodes, so this would be a hyperparameter, a set of P1 unary operators, so cosine, sine, exponent, log. These are things that take 1 input and give you 1 output. A set of P2 binary operators like addition, subtraction, raising to the power, and these are things that take 2 inputs and give you 1 output. And then a set of L leaf nodes containing variables, constants like pi, or p, as apparently it's actually said in Greek. I'm going to stick with pi for now, though. And then integers in the range -10 to 10. So these are the building pieces they use to generate these trees. And then the trees they are expressing as a string using Polish notation. I think this is Polish notation. They're expressing them as a string so that each tree has 1 string that maps to it, and each string maps to 1 tree, blah, blah, blah. So it's a 1-to-1 mapping. And then these are being used as the input to a NLP deep learning thing, and I don't think we've quite gotten to what that is yet. And then the authors said that the results of this were better than those provided by Mathematica or MATLAB, I think they said, although they're, Mathematica and MATLAB, and I'm not entirely sure what their evaluation criteria is going to be, because they should, if they are solving the same equation and getting the same answer out, then I would say that they're sort of equal. So I'm guessing there's going to be some sort of, what's the word I'm looking for? Time component to it, maybe, or maybe they don't always get the right answer. So that's also a possibility. let's hop in to the paper, and I believe we had gotten to section 3.4, data set cleaning. And if you want to see the first half of the paper, I say half, I think we'll probably, we might finish it today, we'll see. Hello, everybody. So section 3.4, data set cleaning. Remember, this is using generated data. Equation simplification. In practice, we simplify generated equations to reduce the number of unique possible equations in the training set and to reduce the length of sequences. Also, we do not want to train our model to predict x plus 1 plus 1 plus 1 plus 1 when it can simply predict x plus 5, so the simplest possible equation given the inputs. As a result, sequences plus 2 plus x3, so x plus 3 plus 2, and plus 3 plus 2x will both be simplified to x plus 5. So here you would say x plus 2 plus 3, x plus 3 plus 2, and simplifying those down to x plus 5, which would be equivalent in both cases, as they both represent the expression x plus 5. No, that's what you just said. Similarly, expression natural log of x plus 3 will be simplified to x plus 3 cosine of x squared plus sine of x squared to 1. Oh, sorry. The log of... No, yeah. The natural log of e to the x plus 3 will be simplified as x plus 3. Yes, because these two cancel out. And cosine x squared plus sine of x squared simplifies to 1 from trigonometry. That's been a minute. Thank you very much for these videos. Oh, thank you for tuning in. Sorry, I have my mic right in front of the chat, which is a problem that I can fix in my life, and I've done it. On the other hand, the square root of x minus 1 squared will not be simplified to x minus 1, as we do not make any assumption on the sign of x minus 1. So this could be, so x could be positive or negative, I think is what they're saying there, and they can't determine which it is, so they can't simplify it. Oh, sorry, Abhishek says it is not the natural log, the regular log. Thank you. I might need a little bit of help with the math in this. All right. Coefficient simplification. So basically, if there's things that are equivalent, they take the simplest possible one with the least terms. Zai says, hi from Kazakhstan and India. Good morning. Hello. Well, good morning for me. And 10 Blank Bandana says, just want to tell you it's awesome you do the live feeds. Keep it up. Oh, thank you. I'm glad you guys are enjoying them. When I first proposed this series, I genuinely didn't think anyone would watch it, so thanks. All right, coefficient simplification. In the case of first order differential equations, we modify generated expressions by equivalent expressions up to a change in variable. For example, x plus x tan 3 plus cx plus 1 will be simplified to cx plus 1, as a particular choice of the constant c makes these two expressions identical. There was something special about C that we talked about previously, and I don't remember what it was. Oh, that's right. They sampled C1, so they dropped out half of the equations where they couldn't solve for C1. So we're already working with a subsample of the generated equations that they generated. Yeah, and SJ says x minus 1 could have been positive or negative. Okay. Hi from Russia. Hi from the United States. And Alan says it is natural log based on the simplification they're stating in the paper. Okay. I guess they're choosing one notation over the other. And Abhishek says differentiate it and it will be 0. So this guy here. Okay, helpful. We apply a similar technique for second-order differential equations, although simplification is sometimes a bit more involved because there are two constants, c1 and c2. For instance, c1 minus c2 x divided by 5 plus c2 plus 1 is simplified to c1x plus c2. Well, this guy can be expressed as this guy. Okay, so they're just taking the most simplified version of their equations so that they are less long, it sounds like, and also to make sure that they don't have a huge training set. Which is interesting. I feel like my intuition is that from a data augmentation standpoint, having a larger number of unique possible equations would actually be better, but I don't know that that's actually the case, so. We also perform transformations that are not strictly equivalent as long as they hold under specific assumptions. For instance, we simplify tan square root of c2 plus x plus the cosine h, c1 plus 1 plus 4, to c1 plus tan c2x, although the constant term can be negative in the second expression, but not the first one. Okay, they don't say what the assumptions are, though. Maybe they will when we get a little bit later into the paper. Finally, we also remove invalid expressions from our data set. For example, expressions like log of 0 or square root of negative 2. To detect them, we evaluate in an expression tree the values of subtrees that do not depend on x. If a subtree is not evaluated to a finite real number, e.g. negative to positive infinity, or a complex number, we discard the expression. Okay, so this is how they're modifying their generated equations to make them more tractable, maybe? All right. Experiments. Section 4.1, dataset. For all considered tasks, we generate data sets using the methods presented in section 3, which we talked about earlier, with up to 15 internal nodes, and they have sampled the trees in such a way that the structure of the tree should be varied, so they won't all be right-leaning or all be left-leaning or all be balanced. There should be a variety of different tree structures. L equals 12 leaf nodes in the union of the set of negative 5 to 5, I think. P2 equals 4 binary operators, addition, subtraction, multiplication, and division, and then 15 unary operators, exponent, log, square root, sine, cosine, tangent, arcsine, arccosine, arctangent, sine h. You don't know what makes it an h. Cosine h, tan, sine h negative 1, cosine h negative 1, tangent negative 1. Yeah, I don't know what the h means. But it's a unary operator, and they're adding it to the set. To produce meaningful mathematical expressions while generating expressions, binary operators are sampled with higher probabilities than unary functions. So they're going to get more addition and subtraction than they are exponents and logs, etc. Additions and multiplications represent, on average, half the nodes in our expressions. Oh, interesting. What about... I guess they're saying subtraction is a flavor of addition? Maybe? All right. Model. So here's where I think we'll be more, or at least I will have more background knowledge around the question. For all our experiments, we train a seek-to-seek model to predict the solutions of given equations, i.e. to predict a primitive given a function or predict a solution given a differential equation. And Abhishek is saying that the ones with h on them are hyperbolic. So sine is a hyperbolic sign. Thank you, helpful. Blah, 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 blah. Predict a solution given a differential equation. So they're taking their generated equations and solutions as the training set. We use a transformer model, Vaswani et al. 2017, with 8 attention heads, 6 layers, and a dimensionality of 512. I think that's the same as in the Vaswani paper. Or at least it's very similar. It's not much bigger, for example. In our experiences, using larger models did not improve the performance. Interesting. That is not typical in machine learning problems. We train our models with the atom optimizer with a learning rate of 10 to the negative 4. Oh, constant learning rate. Spicy. We remove expressions with more than 512 tokens and train our model with 256 equations per batch. Sina says, what is the situation where this topic is used? Really only for solving, differential equations and also doing symbolic integration. So it's a pretty narrow use case. At Inference, expressions are generated by beam search with early stopping. We normalize the log likelihood score of hypotheses in the beam by their sequence length. So this is similar to how you'd generate parse trees, or at least the last time I looked into the parsing literature, how people are generating parse trees. We report results with beam widths of 1, i.e. greedy decoding, 10, and 50. During decoding, nothing prevents the model from generating an invalid prefix expression, e.g. +2 times 3. So this is invalid because you don't have anything. You should have two nodes after here, and instead you should have two nodes after this because it's a binary operator, but instead you just have the one node here. So that's the problem with this expression. To address this issue, Dreyer et al. Used constraints during decoding to ensure that generated sequences can always be converted to valid expression trees. In our case, we find that model generations are almost always valid, and we do not use any constraint. Actually, I guess it's a smaller search space, because I believe Dreyer is a syntax paper. Right? When an invalid expression is generated, we simply consider it as an incorrect solution and ignore it. So okay, I don't know. Okay, so they're predicting a primitive given a function or predicting a solution given a differential equation. So if you generate an invalid expression at inference time, you ignore it. I guess you can tell if it's correct or not, right? Because it's the generating the solution that's computationally intense, not checking it. But, oh, look, here's the evaluation section. We can answer this question with help from the researchers. And Sholabomi, I'm sorry, I know I did that wrong, says hello from Lagos. Hello. All right, evaluation. At the end of each epoch, or epoch, we evaluate the ability of the model to predict the solutions of given equations. In machine translation, hypotheses given by the model are compared to references written by human translators, typically with metrics like BLEU score, that measure the overlap between hypotheses and references. And I have written a blog post about why BLEU is only helpful sometimes. Evaluating the quality of translations is a very difficult problem, true, and many studies show that a better BLEU score does not necessarily correlate with a better performance according to human evaluation. Also true. However, unlike in machine translation, we can easily verify the correctness of our model by simply comparing generated expressions to their reference solutions. So in that way, it is much easier than machine translation because there is one solution to each equation, which is really nice. Machine translation would be much easier if that were the case. For instance, given the differential equation xy prime minus x plus y with a reference solution x log of c divided by x, that's not a minus, where c is a constant, our model may generate x log of c minus x log of x. We can check that these two solutions are equal, although they are written differently, using a symbolic framework like SymPy. Interesting. So this, I'm assuming this is a Python library for symbolic mathematics. Awesome. I had no idea this existed, but if I were interested in symbolic mathematics, I think this would be a very helpful tool. Akash says I'm late. No worries. The recordings are available. However, our model may also generate xc minus x log of x, which is also a valid solution that is actually equivalent to the previous one for a different choice of constant c. In this case, we replace y in the differential equation by the model hypothesis. If xy prime minus y plus x equals 0, we can conclude that the hypothesis is a valid solution. In the case of integral computation, we can simply differentiate the model hypothesis and compare it with the function to integrate. Of course, it's trivial. I'm sure it is if you have much more training in mathematics than I do. For the 3 problems, we measure the accuracy of our models on equations from the test set. So this is just how they're checking their answers, and they can directly check did they get the right answer because they know what the solution is, which is nice. And we are just getting to section 4.4 to answer Akasha's question. Section 4.4, results. In Table 1, we report the accuracy of our models on 3 different tasks. On the holdout set, on 3 different tasks, on a holdout test set composed of 5,000 equations. So like the other equations, these are generated. Yep. We observe that the model is extremely efficient at function integration with an accuracy of almost 100% even with a beam size of 1. Greedy decoding does not work as well on differential equations. So for differential equations, a wider beam size looked to work better. In particular, we observe an improvement of in accuracy, reading is hard this morning, of almost 40% when using a large beam size of 50 for the second order differential equations. So for the second order differential equations here, the bigger beam helped quite a bit. For the first order differential equations, it looks like an increase in beam size did help, but the biggest jump was from a beam size of 1, greedy search, to a beam size of 10. So, unlike in machine translation, where increasing the beam size does not necessarily increase the performance, in our case, we always observe significant improvements with wider beams. Typically, using a beam size of size of 50 provides an improvement of 8% accuracy over a beam size of 10. This makes sense, as increasing the beam size will provide more hypotheses, although a wider beam may displace a valid hypotheses in order to consider invalid ones with better log probabilities. Okay. So it's interesting. So they're comparing this to natural language, where a bigger beam sometimes doesn't help, which can make sense because sometimes the correct parse of something is very fairly unlikely, just because of the way language works, and that they don't get that effect with symbolic mathematics. Well, this is sort of interesting. Comparison with mathematical frameworks. Abhishek says, phew, went over my head. A little bit. I wish I had brought my coffee in here, but I didn't, and it's too late now, so we're just gonna keep going. Maybe we'll read about beam search next. I think that could be helpful. There's lots of applications, specifically in parsing. We compare our model with 2 popular mathematical frameworks, Mathematica, Wolfram Research, and MATLAB, MathWorks 2019. Prefix sequences in our test set are converted back to their infix representations and given as input to Mathematica. So Mathematica wants the sort of fully specified form and not the sequence form that they're using. For an input equation, Mathematica either returns a solution, rewrites the equation in a different way, meaning it was not able to solve it, or times out after a preset delay. When Mathematica times out, we conclude that it is not able to compute a solution, although it may have found a solution given more time. In Table 2, In Table 2, we present accuracy for our model with different beam sizes, and for Mathematica with timeout delays of 10 and 30 seconds. Because Mathematica times out on a non-negligible number of solutions, the evaluation would take too long to run on our 5,000 test evaluations, and we only evaluate on a smaller test subset of 500 equations, on which we also reevaluate our model. So it's slow. We didn't want to do the whole set, so we did a subsample. On all tasks, we observe that our model significantly outperforms Mathematica. Okay, so it is accuracy that they're looking at here. On function integration, our model obtains close to 100% accuracy, while Mathematica did not reach 80%. On first-order differential equations, Mathematica is on par with our model when it uses a beam size of 1, i.e. greedy decoding. However, using a beam search of size 50, our model accuracy goes from 81.2% to 97.0%, largely surpassing Mathematica. I am wondering, because I don't think they talk that much about their sort of Mathematica's approach. I'm wondering if that information is proprietary, because I know Mathematica is closed source, and it is possible that they just are not making algorithm implementation details public, so they can't talk about differences in the approach, just the sort of overall performance. I'm not super familiar with Mathematica. Like, I sort of know about it, and they have like their own notebooks project thing, but I haven't used it. Anyway, so it's a little bit interesting that they're talking about like that they're not talking as much about what the Mathematica algorithm is doing, and I'm guessing they just sort of don't know. Unless we talked about it last time and I've forgotten about it, which is also possible. Similar observations can be made for second-order differential equations, where beam search is even more critical since the number of equivalent solutions is larger. For Mathematica, the performance naturally increases with a timeout duration. For each task, using a timeout of 30 seconds improves the test accuracy by about 4%. Over a timeout of 10 seconds. Our model, on the other hand, typically finds a solution in less than a second, even with a large beam size. Wowee. Okay, that's a massive speed up. On average, MATLAB has a slightly lower performance than Mathematica on the problems we tested. All experiments are run with Mathematica 12.0.0.0, and MATLAB R 2019A. I think the R is for the research version. Javi says, the best book. It depends. It depends what you're looking for. The best book about NLP, a lot of people like Elements of Statistical Learning. I find it a little hard to follow. It's very, very math flavored. But that's a recommendation. There you go. All right, table 2, comparison of our model with Mathematica and MATLAB on a test set of 500 equations. So MATLAB is coming in at 65.2% on integration. It looks like they didn't do differential equations. Mathematica tops out at 80% accuracy over 30 seconds, and in less than a second, this transformer-based model gets accuracy in the 98 to 99 percentile range. Percent range, which is a pretty substantial improvement, I would say. And then differential equations, pretty much the same story. If Mathematica is given longer to run, it does better. But with a large beam size in particular, this transformer-based model does substantially better. So, interesting. Mohammed says, I think you really need your cup of coffee. Yeah, it's in the kitchen. I'll go get it after this. All right, table 2, comparison. Nope, we read that one. Table 3, examples of problems that our model is able to solve on which Mathematica and MATLAB were not able to find a solution. For each equation, our model finds a valid solution with greedy decoding. So that's the beam size of search 1, so the least accurate of their 3 beam sizes. There they are. I'm not reading those. All right. Table 3 shows examples of functions that our model was able to solve, on which Mathematica and MATLAB did not find a solution. Thanks. That's just exactly the same as what was in the table text. The denominator of the function is to integrate negative 16 x to the 8 plus 112 x to the 7th minus 204 x to the 6th plus 228 x to the 5th minus x4 plus 1, which can be rewritten as 1 minus 4 times x to the 4th minus 14 x to the 3rd plus x to the squared. With the simplified input, there's the simplified input, integration becomes easy and Mathematica is able to find the solution, but not with the expanded denominator. So what they're saying is that once the input has been simplified, and if you will remember, they did do simplification as part of their... Was it just the inference or the training? Because they did do quite a bit of heavy lifting with the simplification that we just read about in the data cleaning. We simplified generated expressions to reduce the number of unique possible equations in the training set and to reduce the length of sequences. Okay, so they did do simplification as part of the training, but it seems like the trained model was able to handle non-simplified equations at inference time. Whereas Mathematica was not able to handle the non-simplified version, but was able to handle the simplified version, suggesting greater flexibility in their model, although these are 3 cherry-picked examples, which is always a little bit like, could use a little bit more context there. Javi says, only caffeine, 100% pure. Like those little, in the United States, at like truck stops, they'll sell like just pure caffeine pills right by the cafe register, the cash register. And once on a band trip, somebody took like 3 of those and thought they were gonna die. So don't do that. That's my aside, is don't take too many of those. All right. Equivalent solutions. Do we work on this one? No, we haven't. When comparing with MATLAB and Mathematica, we work from a data set generated from our model and use their standard differential equation solvers. Different sets of equations and advanced techniques for solving them, e.g. transforming them before introducing them into the solver, would probably result in a smaller performance gap. So they're suggesting that if they did some of the same data preprocessing that they did during training of their model, and then passed it to the solver, they'd probably the Mathematica and the MATLAB solvers would probably do better. And Abhishek says something is wrong with the denominator. I'm assuming the second parenthesis is supposed to go right here. So it should go bup, bup. I don't know that that's the case, but that's my assumption. The other thing that might be wrong is that all of this should be removed. I'm assuming that they've written this in LaTeX and then it's been compiled, and LaTeX equations, especially big ones, are pretty hard to read. So I'm guessing that they made a whoopsie. And this is, as I remember, it's a submission, so presumably the reviewers would pick that up, and if it gets published, that will be corrected. All right, equivalent solutions. An interesting property of our model is that we are able to generate solutions that are exactly equivalent, but written in different ways. For instance, we consider the following first-order differential equations along with one of our solutions, as you can see. In Table 4, we report the top 10 hypotheses returned for our model for this equation. We observe that all generations are actually valid solutions, although they are expressed very differently. They are, however, not all equal. Merging the squared roots within the first and the third equations would give the same expression, except that the third one would contain a factor 2 in front of the constant c, but up to a change of variable, these two solutions are actually equivalent. This guy. The ability of the model to recover equivalent expressions without having been trained to do so is very intriguing. This suggests, I'm assuming, that some deeper understanding of mathematics has been achieved by the model. No, I beg to differ. I think it suggests that the model has captured some statistical qualities in mathematical equations, but I don't know about deeper understanding. This sort of feels like some mathematicians got sort of interested in machine learning and built a little project, and now they're excited about it. That's not fair. This isn't a little project. This is a pretty complex research project, but it does read a little bit more mathy and a little bit less machine learning-y, if that makes sense. It's got sort of like a disciplinary flavor to it. I don't mean to imply that the work is trivial. All right, and here we have some equivalent expressions. And the scores are generated by blue. So I believe that these are blue scores. Does they say? Top 10 generations of our model for first order, blah, 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 generated with beam search. All hypotheses are valid solutions, and they are equivalent up to a change of the variable c. Scores are log probabilities normalized by sequence length. So they must be log probabilities given the training data set, which is generated, and was generated to have a wide variety of equation structures in it. So it's not especially biased towards any particular equation structure, but it does prefer shorter equations. Abhishek says it sounds more of differentiation and integration. Yeah, I would say that this is a paper where the main focus is the task and not the method necessarily, that's good. I like a good task-based paper. All right, section 5. And they did that thing where I know that this is discipline specific, but they did that thing where the related works at the end, and it's not my favorite. Y'all have heard me say that before. All right, section 5, related works. Computers were used for symbolic mathematics since the late 1960s. Moses, 1974? I would guess, were it me, I probably would have picked a paper from the late 1960s, although that might be like a review paper about like the work that we've done in the last decade. Computer algebra systems, CAS, such as Mathematica, MATLAB, Maple, Perry, and Sage I have heard of, are used for a variety of mathematical tasks. Modern methods for symbolic integration are based on Risch algorithm, Risch 1970. Implementations can be found in Bronstein and Geddes et al. 1992. However, the complete description of the Risch takes more than 100 pages and is not fully implemented in any mathematical framework. Okay, so when I was like, what is Mathematica and MATLAB using and why aren't they talking about it? So it must be a partial implementation of this solving algorithm. Deep learning networks have been used to simplify tree-like expressions. Zaremba et al. Use recursive neural networks to simplify complex symbolic expressions. They use tree representations for expressions, but provide the model with problem-related information. Sorry, I just completely blanked out. Zaremba et al. Use recursive neural networks to simplify complex symbolic expressions. Okay. They use tree representations for expressions, but provide the model with problem-related information, possible rules for simplifications. So this is sort of a hybrid system that has rule-based expert system components and then also a neural network component. Isoptaliator, I guess, on Twitch says, is this the same paper as last time? It is the same paper as last time, and we are almost done. The neural network is trained to select the best rule. There's a system out of Stanford called Snorkel that does something similar, except that instead of selecting a single best rule, it selects a weighted combination of rules. It's called Snorkel. Did I say that it was called Snorkel? It's called Snorkel. Isoptaliator says it's like opto-isolator, but wrong. Okay. Helpful, I guess. No, that is helpful. Where were we? Alomanis et al. Propose a framework called neural equivalence networks to learn semantic representations of algebraic expressions. Typically, a model is trained to map different but equivalent expressions, like the 10 expressions proposed in Table 4. To the same representation. However, they only consider Boolean and polynomial expressions. Most attempts to use deep networks for mathematics have focused on arithmetic over integers, sometimes over polynomials with integer coefficients. For example, Kaiser and Sutskever 2015 proposed the neural GPU architecture and trained networks to perform additions and multiplications of numbers given in their binary representations. They show that a model trained on numbers with up to 20 bits can be applied to much larger numbers at test time while preserving a perfect accuracy. Additions and multiplications of numbers given their binary representations. A model trained on numbers with up to 20 bits can be applied to much larger numbers at test time while preserving a perfect accuracy. Maybe I'm missing the point of this, but do you need a neural network for this? For just like addition? Maybe it's because the numbers are so big that they won't fit in memory or something? I'm not saying it's not interesting research, I'm just confused. Oh, okay. I think they're just saying that it's the GPU architecture. No, they definitely say training networks. It's definitely some sort of deep learning. Fascinating. If I had infinite time, I would go and read that paper, but probably I won't. ISWAP Talator says, yep, I'm lost. Are they faster? If someone's read the paper, please feel free to chime in. Or at me on Twitter. Applied to much larger numbers. There we go. And Freivalds and Leipens, 2017, proposed an improved version of the neural GPU by using hard nonlinear activation functions and a diagonal gating mechanism. Abhishek says, I saw they were using 250 equations somewhere. The Kaiser and Sutskever paper. Saxton et al. Use LSTMs, citation for LSTMs, and transformers on a wide variety of problems, from arithmetic to simplification of formal expressions. Okay, this might be one of those things in math that I'm like, I know what a number is, and I don't know what a number is. And maybe it's like, I know what addition is, but I don't know what addition is. And it's actually way more complex than I think it is. That's gotta be. There's gotta be some complexity that I'm not getting here about why you would use a transformer to do addition. Or any neural network to do addition. There's gotta be something else going on. However, they only consider polynomial functions and the task of differentiation, which is significantly easier than integration. Trask et al. 2019 propose the neural arithmetic logic units, a new module designed to learn systematic numerical computation, and that can be used within any neural network. Neural arithmetic logic units. I wonder if this is like a forget gate in an LSTM, maybe? Like Kaiser and Sutskever, they show that at inference, their model can extrapolate on numbers orders of magnitude larger than the ones seen during training. All right, conclusion. In this paper, we show that standard seek-to-seek models, I guess transformers are standard at this point. ISO says, speaker, I've created a computer program which can do addition of large numbers. Audience. Okay. I'm sure it's much more interesting than it sounds to me, someone who is not in math. In this paper, we show that standard seek-to-seek models can be applied to difficult tasks like function integration or differential equation. Because there is no existing data set to train such models, we propose an approach to generate arbitrarily large data sets of equations with their associated solutions. Math teachers everywhere rejoiced. We show that a simple transformer model trained on these data sets can perform extremely well both at computing function integrals and solving differential equations, outperforming state-of-the-art mathematical frameworks like MATLAB or Mathematica that rely on a large number of algorithms and heuristics and a complex implementation. Reich, 1970. This is the one that they keep saying is over 100 pages, which I know that in math world is beyond the pale. A 4-page math paper, I feel like, is a pretty long math paper based on my friends who did math. Kushigara says, I probably think the 2015 paper might be to overcome limitation of computers to compute lengthy expressions. Oh, okay, so it's just like the size is what makes it, the size of the like expression that you're adding is what makes it a difficult problem. Interesting. Andy says, apparently Keras has transformer layers now, so I guess they're standard. Yeah, it's interesting. It's been, 2 years, and there's this whole new architecture that is now the go-to for a variety of tasks. Results also show that the model is able to write identical expressions in very different ways. These results are surprising, given the incapacity of neural models to perform simpler tasks like integer addition or multiplication. Okay, so it must not have been integer addition. It must have been, I think they said polynomial, so polynomial addition would be more complex. However, proposed hypotheses are sometimes incorrect, and considering multiple beam hypotheses is often necessary to obtain a valid solution. The validity of a solution itself is not provided by the model, but by an external symbolic framework. Yes. So it's not like reinforcement learning problem. Well, even in reinforcement learning, you usually specify your reward function. These results suggest that in the future, standard mathematical frameworks may benefit from integrating neural components in their solvers. And then references. Okay, so thoughts. Wow, it's been a long time since I've taken calculus. That's my first thought. Wowee. But the things that I think that are really interesting for machine learning practitioners, this may be the first problem that I've run across where they tried larger models and the larger models did worse. And I'm assuming they gave it sufficient time to converge. They didn't really talk about training time, so that might have been a limitation, and a larger model given more time to train might have done better. They also intentionally reduced the size of their training data set, which I'm not necessarily against. I think models that work well on small training data sets are fantastic. I'd love to see more of those. I get that it's because of the way that deep learning works tends to be more difficult, but that was definitely interesting. As a person that doesn't need to do this task very often, I think the thing that for me is most compelling is the, obviously the huge performance increase, or accuracy increase is definitely a important advancement, especially because these are cases where, in addition to a solution, you know whether or not the solution is correct. So that's having like not 100% accuracy is fine because you have like a definitive answer, like, is this the right thing that you did? But the thing that I think for me is most intriguing and as a user would be most compelling is that these take 1 second and these take 30 seconds. And if I were doing a large number of equations for whatever reason, I would want the faster one that worked better. So it's sort of a machine learning application. I think there's good evidence that this does in fact work, which I'm gonna go on record. I think like last year someone asked me if this was a thing. I was like, oh no, probably not. No, I wouldn't imagine it is. Turns out it is a thing and it does work. So I will eat my words. There. ISO says larger model means more layers or neurons. I'd say both. Generally, when I'm talking about overall size of a model, I'll consider the number of trainable parameters. So I want to say that in the original Transformer paper, there were in the order of millions. Does that sound right to y'all? Like 13 million parameters? Definitely models like BERT and GPT-2 have a lot of trainable parameters. Those definitely are in the order of millions, which is more than I would care to train personally. But that's my my stance. What am I looking for? I'm looking for the link to the Vaswani paper to see if they They didn't have a link, but here we go. If we can see the number of trainable parameters. Different parameters. 12 hours, big models, hyperparameters, different parameters. Yeah, I don't think they say in the paper. But yeah, overall, I would say that I am surprised that this works very well, but also very impressed with their results. And I really like that it's fast. Someone who might want to use it at some point for some reason. I think faster is good. Walter says, awesome paper. Thanks, Walter. It was recommended to me by someone whose opinion I trust. It was Walter. Walter recommended that we read the paper. Actually, no. No, I think it was Jeff that brought the paper up. And then Walter was like, Rachel, read the paper. And y'all voted for it, so we did. All right, I'm going to wrap it up here because I can hear my coffee. Just like, Rachel, come drink me in the kitchen. And we will be back on Friday for some sort of live coding. I'll figure it out when I get there, when we get a little bit closer. And we will be back next Wednesday for another paper. And I might do a poll, or I might just be like, that's it, we're reading EfficientNet. Because it's been in the poll for like 4 months, and I know it's an important paper, and I know we don't do enough computer vision on the channel. So yes, there will either be a poll or we'll just read EfficientNet, one of the two. All right. Thank you for joining, everybody. I hope this was helpful for you, and I will see you on Friday or next Wednesday. Bye.